which we're not because we're already doing that somewhere else. And then bytes 8 to 11 to be the number of public inputs. Again, it's a strange thing that is expected from verifier programs. But if we have a look in here, we are adding our number of public inputs that we defined here to big endian bytes. This word might be familiar to you, or maybe not. If you study software engineering, then you might know what this is. But basically, big endian and little endian are ways to format bytes in memory. And most systems now use little endian because it's just faster. Like Solana uses little endian, and probably your computer does as well. But a lot of crypto, especially zero knowledge crypto, uses big endian. So we got to convert things into big endian bytes. So that's what 2BE is big endian bytes means. So we convert our public inputs into big endian bytes. Then we're converting, this is just a 0, into our big endian bytes because we don't have any commitments to do here. And then we're doing our public inputs to big endian bytes once again. So that is our header, which fills up this 12. And then we can go into the next part, which is actually our public inputs. And all we have to do is add these into our inputs the way that they are here, which is like our Poseidon hash. And we do this needs as ref. These are already the Poseidon hash format, but this one isn't. So we have to do that there. And then because our amount bytes is a little bit smaller, we just have to pad it with a bunch of zeros, which is what we're doing here. We're padding it with zeros and then we're adding it. And then we're just returning inputs. So this is our public inputs now all formatted, ready to go for our verifier. And we just have to CPI into it with our proof and our verifier. So we have got to make sure that we add our verifier to our withdraw accounts, because we're only going to be verifying whenever we're trying to withdraw. So we need to make sure that our withdraw function is aware of our verifier program. So if we head down here into our withdraw accounts, we can see that we have our verifier program here. It's an unchecked account because we don't know what that program actually looks like. So we can't check it. But we are constraining it here by making sure that the verifier program is equal to the Sunspot verifier ID that we identify at the very start of this program. So whenever we do anything with an unchecked account in Anchor, we have to put this here to say that, like, okay, yeah, it's unchecked, but it's safe. So we're already validating it by the constraint here. So now our program is aware of our verifier program, and let's actually call it. So if we go back up to our withdraw function, which is getting to be quite a long program now. It's right here. And we can scroll down and see that So we can scroll down and see that before we do our transfer, we're going to call and make sure that our proof is valid. So what we're doing here is we're getting our public inputs and encoding them and passing in the root nullifier hash recipient and amount that we are getting from the parameters in here. And then we're going to do this instruction data, which is the data that we're actually going to be passing in to do the CPI. And we are doing our proof and we're doing a public inputs. So then we're going to invoke this CPI. We're doing this in a slightly different way than what we did previously when we're calling the system program, because the program that we're trying to CPI into is not an Anchor program. So we have to use this instead. So we just use something called invoke. And it's pretty simple. And then we pass what the instruction is going to be. So we're calling the program ID of the verifier program from the accounts. We're passing in nothing for the accounts. It doesn't need any accounts. And we're passing in this instruction data, which is our proof and our public inputs. And that's going to verify the proof. And if that goes through and everything is verified, then we go to the next part of the code and mark our nullifier as set. Just a bit more information about these CPIs. We use invoke when we're calling another program. The caller's authority is going to be passed through into this one. We use invoke signed to sign with PDAs, for example. So we'll use this when our PDA needs to authorize something, but we're just using invoke here. And we're using invoke instead of CPI context because the program that we are calling is not an Anchor program. Okay, so now we are ready to deploy our program. We've got everything working. We've got our sunset verifier here. We are verifying our proofs. We're making sure we're updating our Merkle tree, and we can actually deploy. So if we head into our Anchor directory, This is an Anchor program, so we can just build it first to make sure everything's good. Oh yeah, we have to sync our keys first. So basically what happened there is that our Anchor, the key here was different from the key at the top that's declared here. So we just run Anchor key sync and then we can sync them all up. Then let's try building it. So we can see in our program that our withdrawals now require ZK proof. Our program calls a verifier before our CPI releases funds. If the verification fails, the entire transaction reverts and no funds can actually move without a valid proof. So let's just wait for this program to be built. Okay, we got some warnings there, but we don't have any errors yet, so. Okay, awesome, it built. That's good. So now we can deploy it to our DevNet. So we do Anchor, program deploy, and pass in the cluster as DevNet. All right, our program's been deployed onto DevNet. I'm going to make sure that we keep this program ID because we're going to be using that in the next step, which is where we wire everything together in our front end. So now we've built all of the individual pieces. We're going to see the complete flow and have a look at how we're calling some of these things and wiring all of them together. In this step, we're going to understand everything about the front end, how it builds and sends withdrawal transactions using Solana Kit. So we're going to be generating our TypeScript client with qwe2. We're going to walk through with the withdraw transaction code, and then we're going to run and test the complete flow with everything all together. So first off, we're going to be generating our qwe2 client with our IDL. An IDL stands for Interface Definition Language. Think of it kind of like a JSON file that describes your Solana program's API. What instructions it has, what accounts they expect, what data types they use. Whenever we ran Anchor build just now, Anchor automatically generates an IDL file by reading our Rust code. And we can have a look at that actually in our target IDL private transfers JSON. This can be used by any front end or script that wants to call your program, can read this IDL to see exactly how to format their requests. It makes it just a lot easier to be doing stuff with Solana. So for example, our IDL will describe our withdraw instruction, and it says that it needs a proof in type bytes, it needs a nullifier hash and all the different types and everything in there. Without this, you'd have to manually figure out how to serialize data correctly and what byte order they use and everything. And that's just a bit tedious and error prone to do. So we're going to be using this IDL with something called qwe2, which is going to generate TypeScript definitions for us and make it super, super easy for us to use this within our front end. So if we go into our front end here, and we can find scripts, generate client. You can find this really easily online on the qwe2 docs. I'm just copying and pasting from there. Basically what we're doing here is we are getting our IDL path that we've specified in here. Then we're creating from root with our IDL path, and we're just saying where we want to put it. So we want to put it in /source/generated. So let's go ahead and run this script by cding in the front end. Again, using bun run scripts/generate client. And if we have a look at our source directory, we've got all the generated stuff in here. So if we look at it, we can just see that it makes it super, super easy to use all this stuff within TypeScript. We have a bunch of functions we can use, a bunch of types that we can look at, and it's going to be much easier for us to do our front end. So before we dive super into the front end code, we're going to need to set some consts here. So let's again get our Sunspot verifier ID from up here. This is not the program that we just deployed, but it's our Sunset program. Okay, I think it should be. Okay, I don't know where it is, but I do know that it is in my Anchor toml here. So I'm going to paste that, copy that, and paste it into our if we go to front end, source, constants, front end, source, constants. Sorry, wait. So if we go to our front end, source, and constants, we've got our Sunspot verifier ID there. And we're just going to change it to this one. And then we are also going to need our program ID to put onto our backend. So we get our program ID from our private transfers. We head into backend. This is going to be generating all of our proofs for us, source and server. And then we'll see something at the top, which is our program ID here. We don't need to do this for our front end because Kodama automatically gets our program ID for us, so we don't have to set it anywhere. All right, let's go back to our front end and we'll head inside our components and have a look at our withdraw section so we can see how we are formatting all of our requests. So we are using something called Solana React hooks. This is going to make it super easy for us to use React. We're using use wallet connection and use send transaction. This is a React hook that gives us the connected wallet, and this is a React hook that helps us signing and sending transactions. Then we've also got Solana Kit, which is what React hooked use under the hood. We've got an address, which is going to convert a base 58 string into an address. We've got get program derived address, or get PDA, which derives a PDA from the seeds and the program ID. We get bytes encoder, which is going to help us create an encoder that converts our strings into bytes, which we're going to use for our withdraw. And then we've got address encoder, which converts an address to 32 bytes, which we're also going to use. And then we're getting some of these things from Kodama as well. So we can actually get an encoder to make sure that we get all of the data correct in our withdraw function. And we're getting our program address for our private transfers. So let's head down here and find our withdrawal proof. So we're getting our withdrawal proof from our backend, and then we're just converting this into the types that we need in here before we call our withdraw function. Then we're going to be deriving some PDAs here. This is super simple to do. We can just get our pull PDA from get PDA. We pass in our program address that Kodama gives us. We pass in the seeds that we have set in our consts. We also need our nullifier set. We pass in the same seeds, and we need our pool vault, which we do the same thing for. And then we need to encode our instruction data into the way that our program expects. This is super simple with what Kodama has given us with get withdraw instruction encoder. So we just pass in our proof, our nullifier hash, our root recipient amount in the same order that's expected from our program, and we just encode it, and then we're all good to go. So now we're actually ready to build the instruction. So what we have to do here is we pass in the program address, and then we give it all the accounts that it needs. So we've already derived these accounts before. We got our pool PDA, our nullifier set PDA, our pool vault PDA, our recipient address, and then we also need our Sunspot verifier ID and our system program ID. These roles specify what is actually going to be done with the account. So if it's 1, that means that it is writable, and if it's 0, that means it's read-only. We can also set 2 as a read-only and a signer, and we can do 3 as being writable and a signer as well. But we just need these ones for now. And also something that we specifically should do for verifying ZK proofs is request more budget for compute, because sometimes we need a little bit more to verify proofs. So what we can do here is just create a new instruction. We're going to call it compute budget instruction. We'll pass the compute budget program ID that we've set in a const. It just looks like this. We'll pass the accounts, which is nothing, and then we pass the data, which we have set up here. Basically, the only important thing that we need for here is how much compute units we're actually wanting, and we're going to request this many. That should be enough. And then we can send the instruction. First thing we want to do is just make sure we get that compute, and then we'll send the withdrawal instruction. I think we are ready to run the front end. Let's head back to our terminal. We're going to first run into our backend, because our backend is actually going to be the one that verifies our proofs. We'll do bun run dev. Oh, we need to install first. Whoops. Bun run dev. And then we will open our front end and bun run dev into here as well. I think we've already installed. All right. So we head back to our browser. This is it open here. I've already connected with my wallet previously, and we can deposit. Let's zoom in a bit. Let's deposit 0.2 sol. So we're generating the note here. I have to sign this in my wallet. This isn't a real wallet, so it's fine. It's going to say that it won't succeed. That's because we don't have any sol on mainnet, but we do on testnet. So it will succeed. Okay, so now we've got our deposit note, and this is what we need in order to withdraw. So if we paste this deposit note into withdraw, we can see that this is the amount that we want to deposit, and we can hit withdraw. This is generating our proof right now. It doesn't take much time to do it with Gross16. It's pretty fast. And then we've got our 0.2 sol. So we have just deposited into our pool privately and then withdrawn also privately. And there you have it. You've built a privacy-preserving transfer system on Solana using zero-knowledge proofs. We built a private transfer pool where deposits are hidden behind cryptographic commitments, withdrawals reveal nothing about which deposit is being spent, and double spending is prevented without revealing identity. We practiced anchor macros, CPIs, PDAs, and we learned a little bit more about Kit. We also generated a ZK verifier, learned about ZK verifying, and a bit more about Solana compute budgets and transaction sizes. And we learned best practices when it comes to handling ZK and privacy on Solana, all about Merkle trees, commitments and nullifiers, Poseidon, and how to keep things private on a public ledger. Congratulations, and I hope you enjoy the rest of the bootcamp.
In this project, we're going to build something that powers billions of dollars in transaction volume on Solana. A fiat-backed stablecoin. If you've ever used USDC or USDT, you've interacted with this exact type of system. So what exactly is a fiat-backed stablecoin? It's a token where every single coin in circulation is backed one-to-one by real dollars, sitting in a bank account or treasury bills. When someone deposits $100, we mint 100 tokens. When they want their dollars back, we burn the tokens and release the funds. Simple concept, but building it correctly requires understanding some critical Solana concepts. Here's what you're going to learn. First, we'll dive into Token 2022. It's Solana's modern token standard designed to build tokens with real on-chain rules, advanced control, and features like freezing, burning, and role-based access. Token 2022 has several different extensions that you can add onto a token for various use cases. Specifically for this project, we're using Token 2022 to be able to meet regulatory compliance needed to issue a stablecoin. For example, if a sanctioned wallet is holding your stablecoin, regulators expect you to be able to freeze or seize those assets, and Token 2022 enables this feature. Second, we'll learn about program-derived addresses, or PDAs. Our program uses PDAs as the mint authority, which means no private key controls the token supply. The program itself is the only thing that can mint, and it only does so when the rules are followed. Third, we're implementing a minter allowance system. Not everyone can mint tokens, only authorized minters, and each one has a cap on how much they can create. This teaches you how to build role-based access control on-chain. Fourth, you'll build emergency controls, a pause mechanism that stops all minting if something goes wrong. Real stablecoins need circuit breakers, and you'll understand exactly how to implement one. The patterns you learn here are similar to those used by actual stablecoin issuers, so let's get to building. Before we build our stablecoin, let's make sure we understand how tokens work on Solana. So there's two account types that you need to know. First, there's the mint account. This defines the token itself. Think of it like the definition of a currency. It stores the total supply, the number of decimals, and who has the authority over it. There's only one mint account per token. Now, second, there's the token account. This is where tokens are actually held. It's like the wallet for that specific currency. It tracks a balance and points back to its mint, but also its owner. There can be millions of token accounts for a single mint, one for every user holding that token. The simple way to remember this, the mint is like the currency definition, and the token account is a wallet that's holding that currency. Solana has a built-in program for handling tokens called SPL tokens. If you're familiar with Ethereum, this is Solana's equivalent to ERC20. It handles the basics, like creating mints, minting tokens, burning tokens, and transferring between accounts. It's been around since Solana's early days and works great for simple tokens. But this is where token extensions comes in. It's also called Token 2022, and it's a superset of the token standard that's backwards compatible with the SPL token, but it adds powerful new features called extensions. There's over 15 different extensions available today, and a token can mix and match with different extensions as you see fit. For example, if I'm creating a subscription service and I can have a website that is token gated, but you must own the subscription token to be able to access it. So for this to work, I would create this token with an extension like non-transferable and permanent delegate enabled. So when someone signs up for the subscription, I'll mint a token to their wallet and they won't be able to transfer it. And this validates that the holder has actually successfully signed up for the subscription. Then if the user stops paying for the subscription, the permanent delegate can then go and burn their token, revoking their access to the subscription service. Now for this project, it's a stablecoin. So a stablecoin would use token extensions to ensure regulatory compliance. So here's some extensions that we could use for our stablecoin. There's permanent delegate. This lets an admin transfer or burn tokens to any accounts. And why would you want that? Well, for compliance, sanctioned enforcements, legal recovery, real regulated stablecoins, they'll need something like this. There's also default account state. New token accounts can start frozen or unfrozen by default. This gives you control over who can actually hold your tokens. Then there's metadata. You can store the token's name, symbol, and image URI directly on chain. So there's no external programs that are needed. And then another one would be transfer hooks. So transfer hooks allows you to run custom logic on every single transfer. This enables things like KYC checks, blacklists, or transfer fees. So when we initialize a mint account for a stablecoin, we'll initialize all the extensions that we want to use at that time. And we'll see exactly what that looks like when we clone our code right now. So here is our stablecoin code. And as always, we're going to start with the program state. So we're going to scroll down. Everything here is in one librs file. So we're going to be bouncing back and forth around the file a bit. But we're going to scroll down to where all of our account structures are. And the way that this stablecoin is created, there are 3 core accounts. So the first one is our config accounts. And the config account is essentially like the control center of the stablecoin. And how that works is there's only one config per program. And the reason behind that is because when you're defining the config account when it's initialized, so we're going to go back to initialize and going to the initialize struct where all of the accounts are passed through. When you're defining the config account, you can see here for the seeds field where the PDA is defined, the PDA is just config. So because it's only one word that is a constant, there can only be one config PDA. If there were other variables added, like the payer's public key, then there could be multiple config PDAs. However, here there's only one constant for the PDA, so one config account per program. And this config account is what's going to be, like I said, the control center of the stablecoin. So going back to our account structs, we have our config. And the reason that there's only one is because it's essentially the mint authority and the permanent delegate of the coin, and it signs all token operations via CPIs. So when our CPIs are called within the program, it's going to be with signer seeds, and those signer seeds are going to be the config accounts. So this has the main control of the stablecoin. However, we're going to want to have people being able to have access to mint new tokens and burn those tokens. And we're going to do that by having a minter config and being able to add and remove minter authorities to the program. So that is what this other account is, this minter config account. And what that is just storing all of the information for a minter that is going to have access to mint tokens. So you can see here it's storing the minter's public key as well as how many tokens they're allowed to mint, and then keeping track of how many they've minted so far. So if you're allowed to mint 1,000 tokens, at each token that you mint is going to add as a counter here in this allowed mint field, amount minted field. And then just saving if it's initialized, and then the bump, which we've already went over in the escrow program, why you want to save the bump field in your program state. Okay, so these are the 2 accounts that actually have a custom data structure that's defined here that are holding data on chain. The other account, which is the last core account for this program, is going to be the mint account of the stablecoin itself. And that's not going to have a struct here because it's not going to be holding actual data besides what is in the mint account for a token. And that is created by using the mint instruction with the token program or token extensions program, which we'll be using specifically for this project. So that does not have to have a data structure defined here. So just to recap, you only define this account's structure when you are creating a new account on chain that has custom data that needs to be met. And you're going to specify every field for that data. For mint accounts, all of the data that's stored is already predefined for token mints. Okay, so before jumping into the actual instructions, one more thing to just recap with our config accounts is we have the minter config to enable multiple minters with different issuant constraints and specified amounts over time. So this helps meet a lot of regulatory compliance that's needed for issuing a stablecoin. Now we can dive into the actual instructions themselves. So if we go back up to the top where we have this program macro from Anchor, and then we have our stablecoin that has every function defined here, we're just going to go over high level what each function is, and then we'll dig in a bit deeper where we need to review new concepts that are being learned from this bootcamp. A lot of the concepts are repetitive from previous projects in the bootcamp, so we're just going to not dive too deep into that, but give a high-level overview. So the first instruction here is initialize. And what this does is it basically bootstraps the whole system. So I'm initializing what the config account is and storing all of the data needed for that config account. I'm initializing what the mint is and what extensions that I want added to that mint account. And I'm also calculating how much space is needed for the mint account to be minted and held on chain, and setting up the instruction to initialize a mint using the token 2022 program. Now, the next instruction is configuring a minter. So what this instruction does is it configures a new mint authority on the stablecoin. So if you're adding a new person into the stablecoin that has the authority to mint X amount of tokens, you're going to execute the configure minter instruction and specify the public key, the amount allowance that they have to be able to mint, and then that way the user will be able to execute the mint instruction that we'll show in just a second. And then we have the remove minter instruction, which basically just does the opposite, removing that public key's access to be able to mint tokens. Now, you have this mint token instruction, and typically you can just call mint from SPL token. And anyone that has the correct authority, when you mint it, you're going to be able to just call it. However, the reason we have a custom program here is we want to have specific minters with a specific amount of allowance over a certain amount of time. So to be able to customize that, it's going to be in its own program. So here you can see that there's this require. We're requiring to make sure the stablecoin is active, but there's also a require to make sure that it's the correct minter config. So the correct person with the correct allowance can call this mint instruction. And if you don't have that correct allowance, then this instruction is going to fail. So what sets this apart from the typical mint instruction for SPL tokens is that your minter authority is able to be controlled with an allowance and a time that it's able to mint because of this configure minter account that we have and these instructions that we have as well. So again, this is just to map back to making stablecoins meet specific regulatory compliance that's needed from specific companies. Now, the next few instructions that are here are just additional sanity checks and security checks, like being able to pause the token or unpause it, being able to force burn or force transfer tokens. And these are just again, to meet regulatory compliance. And one instruction that I did skip over was the burn tokens instruction. And the burn tokens instruction is just burning tokens once someone is ready to then receive fiat back for their stablecoin. So just to go back over how this entire life cycle of a fiat-backed stablecoin works is you have a user deposit fiat into a bank account, and then they're able to mint the equivalent one-to-one of what that asset is on chain. So if I deposit $100 into a bank account, then I'm able to mint 100 USDC on chain. And then when I'm ready to withdraw that from the bank account, I am able to burn those 100 tokens on chain and then withdraw from the account. Now, very simple mint and burn mechanism that happens here. However, to be able to have this meet compliance and be able to make sure that the backing stays one-to-one and everything is correctly working, we have these additional authorities and configs set for having minters that have specific access to be able to validate to make sure these transactions are accurate. So now that we've gone over all of the functionality behind the stablecoin and mainly the importance of SPL tokens versus token extensions and where that use case comes in for using token extensions, we can now test the project. So we're just going to run cargo test and let all of the tests run. And this has a pretty developed test suite, just looking at different edge cases, security restraints for the stablecoin. So you can see here there's 23 tests, they all passed. And you can see we have testing initialize, testing if it fails, testing the mint authority, and testing all of the instructions. So the best way to properly understand this program is just going through all of the tests, seeing how they work, and checking out all of the ways to build out a stablecoin. So that's everything for the stablecoin project. If you're interested more in depth of how each one of these functions work and how the derive accounts worked for Anchor when you're passing through all of the accounts that are associated with an instruction, go back to the escrow project because that goes in depth on that section of Anchor and how to write out your instructions and the accounts associated with it. So that's everything for the stablecoin. In this project, we're building a stable swap AMM. Now, you might be familiar with constant product AMMs like Uniswap, where swapping follows the classic X times Y equals K formula. That works great for volatile token pairs, but when you're swapping stablecoins like USDC for USDT, that curve creates unnecessary slippage. You're trading assets that should be worth the same, so why lose value? That's where a stable swap comes in. Originally, it was created by Curve Finance. This design uses a hybrid invariant that flattens the curve near the 1-to-1 ratio. And the result, it's a near perfect swap between stable assets with minimal slippage. In this project, you'll build a stable swap from scratch. We'll implement the core math, including Newton's method for computing the invariant, and you'll understand what that amplification parameter actually does. But we're not stopping at the basics. We'll also implement dynamic fees that protect liquidity providers from arbitrage, a Pyth oracle for real-time price feeds, and depeg detection that automatically pauses the pool when a stablecoin loses its peg. By the end of this project, you'll have hands-on experience with advanced DeFi mechanics, complex on-chain math, and security patterns that separate basic projects from protocols that can handle real value. So let's dive in. So we're going to open up our code for the stable swap AMM. And first, we're just going to go through all of the code that we have because it is quite a lot. So this project is a bit more in depth. So first, we're going to open everything in our source file under the program. You can see there's an instruction folder, and inside this folder is all of the public instructions that exist for the AMM. Now, there's several other files. So we have this constants file that's all of the constants throughout the project, specifically for math or different tokens. We have this dynamic fees section, which is how we're calculating the dynamic fees, all of the errors for the program, the librs, which is where all of your instructions live, a math file, Oracle file, and then state, which is where all of your custom state for the accounts that we're creating for this project exist. So Before we go through the actual instructions for the project, there's two main concepts that I want to go over a bit in depth first. So first we're going to click on this math file, and it's quite long. A lot of different calculations that happen. So we're just going to understand what it is at a high level. And then if you want to dive in deeper, all of this is documented with some pretty in-depth notes explaining where the math came from. But from a high level, we have two main functions. So one is this qwe2 function. So imagine the pool has a health score called D that represents the total value. When you add or remove liquidity, D changes. But when you swap, D must stay exactly the same. And that's the rule that makes the math work. The problem is that the equation for D is too complicated to solve with simple algebra, so we use this technique called the Newton's method. Essentially, it's making an educated guess and refining them until we get close enough. And it's like playing hot and cold, where each guess gets you a little bit closer to the answer. And all of that is explained in the calculations for qwe2. The next one is qwe2. And that is when someone wants to swap a token A for token B. We know exactly how much token A is that they're trading to the pool. The question is, how much token B should they get back? Since swaps must keep D constant, we work backwards. If D stays the same and token A increases by this amount, then what must token B be? The difference between old and new token B is what the user receives. Again, we use Newton's method to find the answer because the math is too complex for a direct formula. So all of that is explained within the documentation for the math RS file. Now, the next concept we're going to introduce in this project is oracles. So oracles are very common in DeFi projects, and I believe this is the first project within the bootcamp that an oracle is being introduced. So we're just going to go over high level what an oracle is and why we're going to need it here. So a smart contract on Solana can only see what's happening inside Solana, like account balances, other programs, transaction data. It has no way to be able to look at the outside world. It can't just Google what's the price of USDC right now or check a news website. So sometimes contracts do need real world information. In our case, we need to know, is USDC actually worth $1? Like on exchanges of Coinbase or Binance. So the solution here is integrating oracles into the smart contract. So an oracle, it's a trusted service that brings external data onto the blockchain. Think of it like a courier who goes outside, checks the real price of USDC across major exchanges, and writes that price into a special Solana account that our program can then read. So for this project, we're using the Pyth network. There's multiple other oracles on Solana, but here we're just using Pyth. So Pyth is a decentralized oracle that aggregates prices from many professional trading firms. Every few hundred milliseconds, Pyth updates price accounts on Solana with the latest market prices. So this project, it needs oracles because we need to understand when a stablecoin is at the correct price or if it depegged. So our pool only knows its internal price. So how much USDC versus USDT is in their vaults. But what if USDC crashes to 90 cents in the real market, while our pool still thinks it's worth $1? That's going to cause arbitrage opportunity. This is creating an unrealistic market for USDC and giving people USDC at the incorrect price that it's not actually valued at. So by checking Pyth Oracle prices, we can detect when a stablecoin has depegged from $1. When that happens, we'll pause the pool or charge emergency fees to protect the liquidity from being exploited. So we have all of those checks in place within this project. But the key takeaway here is that oracles are a bridge between blockchain isolation and real-world data. So without them, DeFi protocols would basically be flying blind. So that's why we'll need oracles integrated into this project. Now let's move on to going through all of the functions that are created in our smart contract. So looking into the instructions, we have initialize pool, which creates a new 2-token pool in the AMM. We have add liquidity or modify liquidity. And what modify liquidity does is both add liquidity and remove liquidity. So adding liquidity is just depositing tokens to receive LP tokens in return. And then removing liquidity is just burning LP tokens to then receive tokens back. Then we have swap, and that is trading token A for token B or vice versa. And then we have check depeg, and that is just a permissionless oracle check, and it pauses the pool if it is depegged. And when I say depegged, I mean it's no longer at the stable value that it's assumed to be. And those are all of the public instructions. So now we're going to start with the state. And once we review all of the state stored in the program, we're then going to go back and do a deep dive into the instructions. So going back to the state file, I always like to start with the state so we understand what data that we're working with and how to take that data to then use in our instruction logic. So here you can see we have 2 accounts. Now let's talk about them. So the first one is our Oracle account. And what this account holds is all of the configuration needed to be able to query a specific oracle from the Pyth network. And here you can see it has Oracle A and Oracle B and their corresponding public keys. And those public keys are how you're able to identify the specific price feed from Pyth for a specific token. So for example, let's say I have a USDC USD pair in my AMM. I'm going to have the public key for the USDC oracle as Oracle A, and I'll have the public key for the USD oracle as Oracle B. And that's then going to be able to query the real-time price feed for both of those assets. So those public keys need to be defined in the config because it's going to then be held in our Oracle config account to then query throughout all of the instructions to be able to pull the exact public key that you're going to use from Pyth. Now, the next field here is a max depeg BPS. And what that is basically just a maximum allowed deviation from $1. So this is how far we'll be able to allow our stablecoin to vary. And if it varies past this allowance, then it's going to pause the pool. And then the next field here is your emergency fee BPS. And what that is a fee to charge when the pool is in a depegged state. So both of these 2 fields are really just to take precautions for any security concerns in case an asset does depeg from its stable asset. And then the last field enabled is just a Boolean, true or false. And it's just a detection if the pool needs to be depegged or not. So if the Oracle data comes back and it surpasses the depeg allowance, it's going to update the Boolean to then pause the pool. So that's everything for the Oracle account. And you see this function here that is really just calculating the length of the Oracle, and what that's doing is understanding how much space that's going to take up on chain. Now, the next section is pool. So what is the pool account? The pool account is just storing all the configuration for a stable swap pool. And it's a PDA seeded by the LP mint address. So the pool is a PDA that owns the token vaults, and because it is a PDA, the program can then sign transfers from those vaults. Now, let's go through all of the fields. We have the admin, and the admin is just the public key of the person that is able to modify the parameters for that pool. Typically in production, this would be like a multi-sig or a governance program. And then we have this LP mint, and what that is the public key for the LP token. So if I'm providing liquidity to a pool, I'll receive an LP token in return. So later when I want to withdraw the liquidity that I'm providing to the pool, I will show the liquidity token to understand how much I provided. That token will be burned, and then I'll be able to receive the tokens that I originally provided to the pool. So this is really just a way to track how many shares I own of the pool and how I can get them back in the future when I'm ready to withdraw my liquidity. Now, the next one is this amplification. And what that is the amplification coefficient that we talked about in the math section. So A is just controls how the swap curve behaves. So if you have a higher A, it's going to have a flatter curve. So the swaps are closer to 1-to-1 when the pool is balanced. If you have a lower A, then it's more curved. So it behaves more like how the Uniswap protocol works. So typical values you would see here, like if you're using USDC or USDT, it'd be about 100 to 2,000. If you're using like staked ETH and ETH as a pool, it would be about 50 to 100. So it's a little less correlated than a 1-to-1 USD stablecoin. So the next section is your fee BPS. So what that is your swap fee in basis points. So anytime you make a swap on an AMM, there's a fee that is accrued. And we're just going to have what that is. So all of this really is just the config that you're setting for how you want your pool to be built. The next one is the token mints. So this is an array of public keys, and it's going to have the token mints that you want for this pool that you're creating. And again, the mint is the mint address to the mint account, which is the global information for that token. The next one is the bump, which we know you always save the PDA bump seed to your account state. Then we're also saving the Oracle config. So once the Oracle config is initialized, we're going to take that and save it into the pool, because when the pool is running, it's going to need to be able to query the Oracle. So we're going to need to get the public key of each token's Oracle to get the real-time price feed. And then the last one is just a Boolean if you're pausing the pool or not. So if the asset does depeg, the pool is going to be paused. And this is just a Boolean to mark if it's paused or not. And then the next is just adding additional functions on that account, which is calculating the space, the mints, and how to find the mint index. So that's everything for the state. Now that we understand the state, we're going to just deep dive into a few key points in the code. So you have all the code, it's all documented, and a lot of this has built off of all of the previous projects in the bootcamp. However, there are a few specifications that I do want to talk about. So the first one is just key validations that happen within this project. So when we initialize a pool, there's a few validations that take place. So I'll open up the initialize pool instruction, and we're just going to search for it. So we have this require for amplification. So this is just making sure that your amplification, your A value, is going to be a reasonable value. So it's making sure that it's positive. You need your A to not be too large and also not be a negative value. So this is just validating that, making sure all of our math checks out. The next one is our fee BPS. So this is just a sanity check to make sure that a fee doesn't exceed 100%. So maybe someone accidentally put the wrong decimal value. This is just making sure that that doesn't happen and returns an invalid fee if the fee is above 100%. And then one other validation check to go over is validating if the volts are correct. So let's find that one. So here, we have the volt validation. So the volt must be the correct associated token account for the owner of the pool and the mint of the token. And this is just critical for security. So we want to make sure that if we accept tokens as the vaults, then it is the correct owner. So it has to be an associated token address. And the reason is because ATAs are deterministic, meaning it has a specific owner and a specific mint, and there's only one valid address for an ATA. So you can see here, there's even a note in the code specifying that if we do accept any token account as the vault, the attacker could pass their own token account as the vault. And when users swap tokens, they could go to the attacker instead of the pool. So very important that we're using an ATA here because it is a deterministic address. So the next thing we're going to go to is the swap section. So this swap instruction, this is the core flow of your AMM. So here we have to get the current reserves of the vaults, and then you're going to calculate the dynamic fee, which is the fee that you want to charge when you're making a swap from the vaults. And then it's going to do all of the swap math that we talked about at a high level that comes from this math.rs file. And then lastly, it's going to do a slippage check. And that slippage check is just making sure that the amount out is larger or equal to the minimum amount out. So that is the core logic for how our AMM is going to work for a stable swap. Now, the next section that I want to talk about is that we have PDAs signing for the vault transfers. So I want to find that function to show you. If we go here and we do token transfer, I believe it'll come up. Here we go. So here you can see when we're transferring out of the vault. So there's two transfers that happen in a swap. You have transfer in, and this is just a regular CPI because anyone is able to transfer tokens into the vault. So I could connect my wallet and deposit. Now, when I want to get tokens out of the vaults, it's going to have an additional security check. So this may sound familiar to you because this is exactly how we designed our escrow program earlier. But if I go here to transfer out, when we're calling the CPI, instead of just new, it's do assigner. And it's new assigner because the vault is who has authority to be able to transfer tokens out of the pool. And the vault is a PDA. So it has to be signed by the PDA to be able to transfer tokens out of the vault to the user that's requesting them. Now, this goes back to the same logic we talked about in the escrow program, where the vault has a PDA signer, and this way we don't have an attack vulnerability for having a private key being able to sign this transaction. It is only the code itself can sign with the signer seeds of the PDA. So here you can see we're making a CPI call with a signer. We specify the signer seeds, and those signer seeds are exactly what the PDA is for this vault. So the pool owns the vault, but it can't hold a private key. So we use PDA seeds to let the program sign on behalf of the pool. And if we go back to the state file, sorry, not the state, initialize pool. And here we go. So we're in the initialize pool file. If I go to the derive accounts macro, this is where all of the accounts that are passed through for the pool are specified. And you can see here for the pool, it is defined with these seeds. And those are the seeds for the PDA of the pool. And if you go back to our swap, so we'll go back to the token transfer, and the transfer was signer. So you can see here, the signer seeds, you have an input parameter for the transfer out function of your signer seeds, and those are going to have to match up with the PDA signer seeds of the pool that we just defined. Okay, now one more feature to go over here is when we remove liquidity from the pool. So I'll go back to modify liquidity, and I'm just going to search for this calculate withdrawal amounts function. And we'll talk about what it does. So this is a function for when you're withdrawing from the pool. And what this is calculating is exactly what will be withdrawn. And this function is specifying that you always get back proportional amounts of both tokens. So there's no single-sided withdrawals allowed in this implementation of the AMM. So if I am depositing USDC and USDT, when I go to withdraw and burn my LP tokens, I am going to receive proportional amounts of both USDC and USDT back in my wallet. Now we're going to talk about just 3 advanced features that have been implemented into this AMM, and then we'll be able to wrap up our whole overview of this project. So the 3 features we want to talk about is first, the dynamic fees. So you can see there's an entire file talking about dynamic fees. So why did we implement dynamic fees? This function was implemented to be able to deter arbitrage on the projects. And that's because an arbitrager knows the true price and they'll extract value from LPs. And this happens when an asset depegs, a pool is imbalanced, or a large swap occurs. And by having dynamic fees on the project, this makes toxic arbitrage very expensive, and then it compensates LPs for their informed trades. So this just helps make a more healthy AMM. Now, the next that we're going to talk about is depeg protection. So there's a function when you're checking oracles, and it's going to be called check depeg. So let's find that. And here's the function. And what this does is it is checking to see if the asset has depegged from the stable price that it should be. And if it does, then it's going to pause the pool to stop trading, which again is going to deter arbitrage that is toxic in the AMM. Now, anyone can call this. So if USDC goes to 90 cents, the pool will pause and it will start charging 5% in fees. And this is just going to protect LPs from getting the pool drained. The next topic we're going to talk about is the remaining accounts pattern. So if I open up the swap RS file, you can see I'll go to the derive accounts, and this is where you need to specify all of the accounts that are passed through for an instruction that the instruction is going to interact with. And Anchor requires fixed account counts at compile time, but we do want to have flexibility for variable token accounts. So here you can see we only have for the swap, the pool, the user, and the token program. We're missing vaults and user ATAs. So that is going to be as a remaining accounts. So when you are writing out in your context, you can call remaining accounts, and that is going to be able to pull in vaults and user ATAs. So you can see here, when you are calling the swap function, we have this remaining variable, and that is pulling the remaining accounts from your context. So here, the remaining accounts for a 2-token pool is going to be your token A vault, your token B vault, your user input token accounts, and the user's output token account. So all of that is going to be under Anchor's remaining accounts function. So this pattern, it lets us validate accounts at runtime while keeping the instruction flexible for multi-token pools. And that is all of the features that I wanted to go over for the project. You can see here throughout the project, everything is documented with an in-depth explanation. And a lot of this does refer back to previous projects that we've worked on throughout the bootcamp. So we've just talked about all of the new logic that was introduced specifically for the Stable Swap AMM project. And that is everything here. And check out the project, build it, and run your tests.
GM, this is Mike, the APC Dario at Solana Foundation. I'm gonna show you how to build a paid app from scratch using Solana S4.2 template. In this repo, we will focus on client-side development. If you are new to the S4.2 protocol, I highly recommend you checking out Jonas Han's video, the new error code S4.2. Okay, just kidding. But seriously, it's a great intro to S4.2 and AI agent payment. So why do we even need an AI agent payment standard? Imagine this, you see a really interesting article on your feed, you click it, and boom, it asks you to pay a 12-month subscription just to read one article. Annoying, right? Now think about bots and AI agents. They hit the same paywalls when they try to access data or service on the web. That's where the qwe2 comes in. qwe2 is an open payment protocol developed by Coinbase. It lets website and AI agents charge per request using stablecoins. Here is how it works in simple terms. Your AI agent asks a server for something. The server replies with a price, you pay, and you get what you asked for. No sign-ups, no subscriptions, no long forms. Even better, qwe2 is built directly into the normal web traffic, HTTP, so it works with the internet the way we already use it today. In theory, this means you could pay just a fraction of a cent to read one article, instead of buying yet another full subscription. Now that you have a basic idea of what qwe2 is, if you are interested in what qwe2 ecosystem on Solana looks like, jump in here at solana.com/qwe2. So how does it work? qwe2 is actually part of HTTP protocol, and qwe2 mini payment is just plain HTTP request. First, client hits your URL, and then you reply qwe2 payment requirement with a JSON payment requirement object. The client pays and retries with a X payment header. You verify and settle, respond 200 and OK. No accounts, no else. Also, take a look of Solana developer guide, Intro to qwe2. You can find a lot more details about the qwe2 ecosystem, like the SDKs, the Explorer, and some real examples in this guide. But today, I just want to show you one thing, how insanely easy it is to build an app with native qwe2 support on Solana. So here's what we're gonna build. Users will pay 1 cent in USDC, and after they pay, they can access an AI fortune-telling service powered by ChatGPT. They just enter their birth information, and the app gives them an AI-generated fortune prediction. That's it, super simple. To build this, we're gonna use Solana developer templates. You can use all of them directly through qwe2 app. If you are new to Solana developer templates, I really recommend you playing with them first. With these templates plus AI, you can save a ton of time and try out ideas really fast. From this example, we're gonna use the Solana qwe2 Next.js template because we got a demo app that already has qwe2 payment support built in. Alright, in this project, we will use Solana qwe2 template. It is a simple Next.js starter template with qwe2 payment protocol integration for Solana. It demonstrates a streamlined integration of qwe2 payment protocol using a library called qwe2 Next, making it very easy to add cryptocurrency payment gates to your Next.js apps. Alright, let's first take a look at the templates. This is the template we're going to use for this project. You can see it's very clear. We got what is qwe2, its features, get started, how it works, and product structure. We can just install it because I already installed all the prerequisites. We can just simply copy it. Here we're gonna jump into this. Okay. You see there's an arrow, but no need to worry about it. We can just see if it's already created. Okay, it's good. Let's come into it. We can just manually install it. It will take a bit time. Great. Right now we got everything installed. Let's take a look of the code. We can first take a look of the template structure. Here we got app and its homepage. Also, we got a layout here and styles. Also, let's go to the content. Okay. Also, there's a component. Also, let's say the most important part here is actually the middleware. You can see we installed the payment middleware function from the Next qwe2 Next library. Okay, as you can see, we got the root for each payment servers. Here we will configure the payment routes using this payment middleware feature from the qwe2 library. And please note the original matcher here is actually match all the paths, which means that this middleware, which is a payment middleware, will be valid to each path except for the static fields. This is where we need to set up the route for the paths covered by the middleware. So we already take a look at the overall structure. We also need to set up the environment here. So we can just set up another one, but call it .env, .local. You can set up the Solana receiver address and also the network we wanna use. So here we're gonna use Solana DevNet for our testing purpose. And you can also set up your facilitator URL. Right now we are using the official qwe2 facilitator. And also you need to set up your CDP API key, because this is from you can find it from the portal of Coinbase developer platform. Here I'm gonna use mine, but we can take 1 minute to set it up. Just give me a minute. Great, it's already set up. Let's take a try. We can run so we can npm run directly after we set up the environment. Great, we can just take a look how it's work. It's need a bit time to get it loaded. We can access no, we are not gonna use MetaMask, but feel free to use it. My used wallet is Phantom. You can choose your favorite wallet to use it, but the default one is actually MetaMask. As you can see, the demo worked well, just as expected. You can unlock your exclusive content or any content here. So you just paid by your wallet right now we use DevNet, so it's DevNet token. So this is what the template look like. Now let's add our own feature and further make this template into a fortune telling app. I already finished the code actually, so you can just check the code link in our description, but also you can try yourself to vibe code it. It's actually very easy to achieve the same features. Let's go through the finished code. Let's take a look at what we create here. Let's go through the app, API, and the root. Here we create a root, which is a post method to receive the birth information we need to get from the user. And also in this post request, we call OpenAI ChatGPT for all mini model to act as the fortune teller and return the fortune results as a JSON file. So this is basically the API here. And also we create 2 pages here. One is a fortune, another one is a pay fortune here. So under the pay fortune here, we actually, it will trigger a payment when user visits the pay fortune page. And it will show this page after a successful payment from our paywall of qwe2, and then provide a button for user to open the feature page. And after user managed to pay it and open the future page, fortune page, we can see the fortune page here. So here we set up like 3 states here. One is birth info, which will accept the user's input, and also we got a fortune to return the information got from the ChatGPT. And also we need to fix a little bit. You can see it's a very, very easy front end. And also we need to fix a little bit about the page. We need to add another button, which is called fortune teller. All right, so this is what the finished code is look like. We can just start to explore it. we still just use npm dev. Okay, we can just go back to net. As you can see here, we got a new fortune teller button. We can just click it and pay now. Okay, it's payment successfully, and let's open the fortune teller. Here you can input your like birth date. I just use a template one. Let's see. As you can see, you got the fortune result as a JSON file from the ChatGPT model. It shows as I gaze into the cosmic energy surrounding your birthday. So it will show you fortune. It's actually a tradition in ancient China, but it's a fun. Lots of people actually believe in it. All right, this is the app we built today. So let's go through the architecture together here. Yeah, we changed the button in the main page, and then like it's actually goes to the pay fortune page. But when I need to go to this pay fortune page, I also need to set up here in the middleware. So that I need to set when I go to this path, I need to set the qwe2 payment is actually routing to this path and make it solid. So after it's got accepted into payment middleware, and it will trigger payment and further show the content from this pay fortune page. And then like when user opens the fortune teller, it will generate the fortune page. And it's in this page, we will gonna call the post request to OpenAI and then get a response from the ChatGPT to get the fortune result. All right, today we'll learn how to use Solana qwe2 to build a payment app on Solana with its native qwe2 support. And also we use a library called qwe2 Next.js here in our project. And also we learn how to integrate third-party APIs. Here we used OpenAI ChatGPT model. Thanks for watching. If you want to learn more about qwe2, how it works, what it is in Solana, feel free to check out the solana.com Next.js page. Looking forward to see you cook with qwe2 on Solana. Cheers! GM everyone, this is Mike, the APACW at Solana Foundation. The most common topics we heard these days is real-world asset. Today, we are gonna explore what is real-world asset, why it matters, and we will also build a RWA app on Solana together. Real-world assets tokenization is a process where an asset is converted into a programmable token. Starting from the stablecoin, more and more assets are gradually adopted to get tokenized on-chain. Now, Solana has over $1 billion daily volume of RWA trading. Solana aims to be the internet capital market, where a distributed internet ledger hosts all finance within a unified liquidity layer. On the sell side, issuers can get the most efficient price discovery with deepest liquidity. On the buy side, asset ownership can be more distributed. Investors open access to all assets, class, anytime, anywhere, enjoy the most capital efficiency. Okay, let's get started to the building part. We will build a demo app to let users mint real-world asset. The app will be a Labubu mystery box on-chain. It allows users to mint Labubu as non-fungible token on Solana. Please note that Labubu we mentioned here is just used as a demo example for educational purpose. My favorite Labubu collection series is Lazy Yoga. In Lazy Yoga, there are 11 types, including 10 common ones and 1 rare hidden one. In our example, we assume to have 120 Labubus for each common type and 6 Labubus for the rare type. So in total, we will got 1,206 Labubus in our inventory. We also need to create a token program for each Labubu type. We need to use token 2022 as a token standard and using Kodama CLI to generate client's code for building the app. I already finished the starter code with a mock front end and a finished program. You can find the repo in the linked description. The starter code is based on qwe2 app templates with Next.js as a front end and Anchor and Kit as a tech stack of Solana. You can find the original templates in Solana developer templates. Let's take a look at the starter code. Alright, first let's take a look at the overall code structure. It's actually a very basic Anchor code. Here you can see we got program and with the SRC and IRB for the Rust program. And also we got a test here. And also we got a Next.js app. You can see the front end with the components and a basic page. So let's go to the IRB.rs, which is our program file first. You can see the overall structure here. We got the necessary imports. And also we got 3 core instructions, which is initialize collection, create a bubble mint, and the third one is mint random. Also, we got the data structure here. If you see the line a little bit below. Also, we got a solid account validation logic here. An error definition we customize here. First, let's take a look at the 3 core instructions. The first one is initialize collection. In this instruction, we initialize an inventory array called collection for the Labubu series, and collection will be used as a PDA account later. And you can see the second instruction is create Labubu mint. Here we create a token 2022 mint for each Labubu type. First, we validate the ID is valid, and also we calculate the rent, and then we create mint account using system program, where it's actually trigger a CPI, which is cross-program invocation. And finally, we initialize the mint using the token program, which is initialize mint2. Here we define it is an NFT because it's indivisible. Third, let's take a look at the mint random instruction, where we will mint a Labubu NFT to a user. First, it will also validate the ID is valid, and the inventory is also valid. We need to decrement the inventory by 1. And then we have PDA to sign. We use collection PDA as a mint authority here. And finally, we update the state. If you see it overall, actually, this is a program where we use CPI. Is that first we have our vault program to cross-program invocation call our system program to create account. And further, we use CPI call to the token program, which you can see we use initialize mint2 and also mint2 user. Alright, after we have a basic understanding of the program, let's go through the code generation part. Right now, we already have our program ready. We need to use Anchor build to build the program. Let's go to Anchor file first, and then Anchor build. In this process, it may need a bit time to really build the program. We need to wait for a while. Alright, now it's finished. Let's take a look here. We're just using Anchor build. So what happens during this Anchor build is that it will compile the Rust code, which we just see, into the binary program. In this process, it will also generate IDL file into a target, which is under target IDL. You can see there is a JSON file here. This one is very important because you can basically interact with any program on chain with its IDL. And also you can find its IDL through the Solana Explorer. All right, let's take a look at the IDL file structure here. You can see the address, metadata, instructions, and data structure, and lots of stuff. And in our next step, we'll show you how to interact with this on-chain program by generating a client using its IDL JSON file. So in this case, we will use Kodama to generate TypeScript client. Kodama is a tool which supports Python, JavaScript, TypeScript, and Rust to generate the client code interacting with the on-chain program. In our case, we will generate the JavaScript code. All right, we will use Kodama CLI tool, which we need to set up the configuration under our root directories kodama.json. Let's take a look. Here you can see we got the IDL path, and also it is a scripts and JS which is a JavaScript code generator. You can see we use JS render here, and also we define the output directory. All right, let's run the generation comment. It's actually very clear. Let's go to the root, and then npm run kodama JS. Bingo is generated. You can see under the app, it's generated a directory called generated. You can see the overall structure here. It has programs, also instructions and accounts, and also the errors we customized, and some shared types here. So what we will need to use is actually we need to interact by using these instructions. All right, so our next step is to integrate our frontend. In our case, we can take a look of what our frontend is like. There are two pages important here. The first one is actually just the same with our Solana template. If you already tried it, it's basically the same. Another one is where we need to customize the front-end logic here to interact with the client code we just generated, which is Labubu card here. So in our front-end, which is client, we use Next.js and React as a front-end stack, and we use Solana Kit as client to interacting with Solana blockchain. All right, let's take a look at the core part of our mystery box component. As you can see, the current starter code uses a mock demo for the blank box. We can first run the npm run dev to take a look. It's already got started. Let's. You can see this is the front-end code which already generated. You can easily generate it like in less than 5 minutes with AI tooling. Here, when you click the Open Mystery Box button, it will generate the Labubu randomly. So this is the basic feature of our frontend. All right, so let's move back to add the real token mint logic to really allow users to mint Labubu on-chain by interacting with the Kodama client we just generated. So here we need to import the function from the generated code, which is this one. Here I used Copilot to help me generate code, but sometimes it's not that accurate. So this function is where we just generated. Here. Let's continue. And also in part 2, we also need to have a list of mint address of Labubu series after we initialize the token mint. We can define it as a mint address. So with this address, user will mint Labubu directly from this mint address. Alright, let's finish the logic. Here we need to define send and sending in our front end. No, we need to use the kit, which is use send transaction here. And also we can define a signature because we can show it in our front end. And then add our logic here. You can take a look of what the basic logic here is. Actually just use our total weight in our inventory, which is in total we got like 1206 Labubus, including like 1200 common ones and 6 rare ones. And also we pick one of them randomly here. We can just continue the logic here. Here we need to get the corresponding mint address first. And then we need to create the object which is used as user signer. And also under this user signer, we have 3 parameters. We got user wallet address and sign transaction, which is the transaction signing function, and also the message signing function. And then we need to create the instruction. And in this step, we need to really use the generated code. Here we need to have user signer, which is the object we just defined. Also mint PDA address. And also Labubu ID, which is a selected Labubu ID. And finally, we need to send the transaction to Solana blockchain. And also we can just directly get the signature because we can show it in our front end. Signature. Here we use send with our instructions. Also, we can set the signature after we finished. And also, potentially, we can set up an alert to see if we are successfully. All right, now we have already finished the front-end part. But remember, we also need a script to get the mint address, right? Because this time it's marked, or our collection account doesn't exist, and our 11 mint address doesn't exist too. So it's a bit tricky here because we also need a test here. Oh, the test field here, although it's called a test, the field is actually a deployment initialization script. The process is like after we anchor build, we also need to deploy, and then we can just run the initialize here, which is a test. The test field has 2 goals. The first is to initialize the collection, And the second is to create 11 mints for each Labubu. We can take a look at the test field here. It got 2 tests. The one is initialize collection. The second one is create 11 mint. So in the first test, it calls initialize collection instruction and create collection PDA account, and then read and verify the account data. And in the second instruction, it will loop 11 times to create a mint for each Labubu type and print each mint address, which is needed in our frontend. Let's take a try. First, we need to deploy it. We can just deploy it to our DevNet. Alright, as you can see here, we got a program ID and signature is deployed successfully. Here it's a bit tricky because usually we need to run anchor test, but here I defined initialize in our anchor TOML here. You can see the initialize actually the run. You can see the initialize actually run the test here. Alright, I just changed another way to initialize it because something went wrong with my yarn here. Right now you can see it's actually already like initialized, and you can see there are 11 address here. So remember we just like marked the mint address here. We need to copy each address. Let's copy it back here. We need to get 11 one. Alright, so already we got the collection initialized, and also we got the front end finished. We can finally have a try of what the current front end is like. We need to run. Let's do it. When I click here, ask me to enter. Bingo! You can see here it successfully minted Labubu with a transaction here, and this is a mystery box I just minted. So in our case, we just use Labubu here for educational purpose. It's not for commercially used. Alright, you can also check the wallet to see there is actually a Labubu here. So why is data here? Actually, you can set up the metadata in the metadata file. Let's take a look of what the current file is like. So here in the metadata, I set up the Labubu with its ID, name, and description, and attributes. Actually, you can also set up this in SPL token with its metadata or token 22 metadata feature. Alright, let's try to summarize it. So in our project, actually we go through the whole process of the program and anchor build into the IDL, and using this idea to generate the client code by Kodama. And with this generated TypeScript code, we further import it into the front end to get integrated and add our core logic to allow users to mint Labubu on-chain. Alright, that's all for the demo app we built for users to mint Labubu RWA. We mint RWA as tokens on Solana through Token 2022 and make a mystery box to allow users to mint RWA tokens themselves. Solana Token 2022 is far more than this. You can explore more about the token extensions on Solana to achieve more features for your RWA, including KYC, freezing and seizing, confidential transfer, and much more. Looking forward to seeing your fun RWA on Solana. Cheers!
Building secure applications on Solana is critical, but surprisingly difficult. Today, we'll cover some common vulnerabilities and how to prevent them. First, you should never trust incoming accounts. This is by no means exhaustive, but there's a laundry list of issues you want to verify. First, is the account owned by the expected program? Is the signer set where you expect it to be? Are the PDAs derived correctly? Is the account already initialized? Did you check for reinitialization attacks? And more subtly, is the account a duplicate of another one? Some of the biggest hacks on Solana, like Wormhole, Crema, and more recently Loopscale, were because of unchecked or incorrect accounts. Anchor's account types provide these checks for you, but you should always be careful and verify the checks yourself if you're using unchecked accounts or if you're writing your own program with Solana SDK. Second, protect yourself against arithmetic errors. By default, Rust won't save you here, and a single overflow or underflow can easily lead to loss of funds. Use checkmath or enable overflow checks. A surprisingly tricky edge case here is around truncation. Even with overflows checks enabled, truncation is by default unchecked. This has led to quite a few high-profile security issues. Third, you should properly validate your program-derived addresses. There's a couple of potential issues here. First, the seeds on PDAs are concatenated together, so if you have variable length seeds, they can collide in unexpected ways with other PDAs. This might cause you to allocate an account, for example, in an address where you expect for another one. Another potential issue is with using non-canonical PDAs. Not everyone knows this, but there are actually multiple valid addresses associated with each set of seeds, because you can pass in different bumps. Anchor by default will handle this for you, but if you're hand-rolling your own program, you should be careful. Lastly, but not least, make sure your program's authority is properly secure under multi-sig, like squads. Many times, smart contract security isn't the only thing that matters. We always recommend using multi-sig with independent signers and hardware wallets. These are just a few of the more common security vulnerabilities you should be aware of when building on Solana. There are many more, and you should always get your code audited before any large amount of funds are at stake in a production environment. Before you deploy on Solana, make sure your application is secure.
So now that we've gone over building applications on Solana, we're just going to do a quick overview of indexing on Solana, what it is and what the best practices are. So indexing on Solana, it's just a way to extract, process, and store on-chain data from Solana. And it enables real-time insights and analytics, and then a way to monitor apps that are live on-chain. So here are some resources. Indexing is going to be different per application that you're building, and these are the resources and best practices to get started for your application. So here is some Helios blogs talking about how to index Solana data. Definitely start there, fully understand what indexing on Solana looks like. One of the challenges with indexing on Solana is finding a way to have high throughput, low latency, and data consistency across distributed nodes. So how do we do that effectively? Well, one way that we can do this is using a Geyser plugin. So that's the fastest way to fetch updates for state transitions and events, and it streams transactions as they're processed in real time. So you can take a look here at the Yellowstone gRPC. And this is pretty simple to use. You can run a validator that's using this Geyser plugin, and this helps you be able to have a faster way to fetch state transitions. Now, Yellowstone, all it is just a geyser-based gRPC interface for Solana, and it's going to help you index a lot faster and more efficient. Then the next thing that we're going to talk about is Carbon. And Carbon is an indexing framework on Solana to help you source account and instruction updates and decoding and then processing the results. So it makes it very, very easy to index on Solana. So it's built to handle different types of updates and route them through the appropriate processors. And the basics of Carbon, how it's going to work, is you choose a built-in data source from the set of crates that are available within Carbon, and then you're going to generate a decoder structs for your program from your IDL. And you can do that with the Carbon CLI, so it's very easy to generate. And then you just implement processor structs to handle the account or the instruction updates that you're looking for. And then once you assemble each part into a Carbon pipeline, you have an indexer running for your program. So this also has very in-depth docs on how to set up your Carbon framework, how to use the CLI, and then there's also ways to implement the processor, and then several different crates that you can work with, and then available program decoders. So all of these very easy to access and then help you get the data that you're looking for. So that is best practices for indexing on Solana.
Since late 2024, prediction markets have entered the mainstream discussion, the most famous ones being Kalshi and Polymarket. Prediction market platforms play uniquely to the strengths of the Solana network, as they benefit immensely from low fees and fast transaction speeds. If you're placing a $5 position, you really cannot afford $1 in transaction fee. Solana makes small stakes viable, allowing everybody to participate. They especially grew in popularity when they correctly predicted the outcome of the 2024 American presidential elections. This election was famously misjudged by professional pollsters, while prediction markets correctly predicted the outcome. Why did the markets get it right? It comes down to skin in the game. Unlike polls, where opinions are free, prediction markets require you to back your belief with money. If you have bad information, you lose money. If you have good information, you profit. Over time, the price moves toward the truth. People sometimes call this the wisdom of the crowds with accountability. At their core, these products offer a really simple premise. You're presented with questions about outcomes. Most of these questions are in the form of a binary outcome, a question for which the answer is the inverse of the other. Let's review a few examples. The price of Bitcoin will close in 2026 above 150,000, yes or no? You pick a side, you stake your money, and you wait. We could create a more interesting contract by proposing different brackets. Let's see an example. The price of Bitcoin will go above 150, but will stay below 200,000. The second question would be the price of Bitcoin will go above 200,000. By composing these binary true or false questions, we're able to find the closest outcome and refine our predictions. Do note that some prediction markets have the capacity to use questions with more than 2 outcomes, but today we will focus on designing with these binary question limitations. This keeps the Solana program logic simple, and they still provide a great user experience. So how do these markets actually work? The mechanics are straightforward. When you take a position, your funds go into a pool. There's a yes pool, and there is a no pool. When the outcome is decided, the winners split the loser's pool proportionally to their stake. Let's say that there's a market with 100 SOL in a yes pool and 50 SOL in a no pool. You put 10 SOL on yes, that means you own 10% of the yes pool. If yes wins, you get to keep your 10 SOL back plus 10% of the no pool. That's 5 SOL profit. If no wins, you lose your 10 SOL and it gets distributed to the no side. This creates a natural price discovery mechanism. If most people think yes will win, more money flows into the yes pool. But that also means that the payout for yes gets smaller. At some point, contrarians see value in taking the other side. The ratio between the pools reflects the crowd's collective probability estimates. This is what we're going to build today. By the end of this lecture, you'll understand how to create a prediction market on Solana from scratch. We'll cover the full stack, from the Rust programming running on-chain to the React frontend that users interact with. On the Solana side, we'll write 4 instructions: create a market, take a position, resolve the market, and claim winnings. We'll go over account design and constraints. We'll look at the validation logic that prevents people from taking position after the deadline or claiming twice their winnings. On the front-end side, we'll see how to fetch all markets from the chain, decode the account data, and display it in React components. We'll use a code generation tool called Kodama that reads our Rust program and generates a TypeScript client code automatically for us. This means we get type-safe instruction builders without writing serialization logic by hand. The architecture might seem like a lot at first, but it breaks down into clean layers. Let's start by looking at the big picture. Let's get an overview of the architecture. This is a full stack lecture, so while we'll go over the program, we will focus more on the integration between applications, signers, and transactions. The front end of our application will use Next.js. We could use totally another React framework or even another JavaScript framework, but Next.js offers an easy way to get started with a good production standard. We'll have stuff like server-side rendering capacities, many optimizations for which we don't want to spend our time setting up manually. The front end will be split between two pages. The first page will show all of the currently active markets. That would be where our Bitcoin above $150,000 example would be, with components allowing users to take position on the yes or no. The second page will be a profit and loss page with statistics on past markets. We'll use this page as an example of how you can display data and present it nicely for users. These components will talk to the blockchain using two easy-to-use libraries that are part of the Solana SDK suite. This will be Solana Client and Solana React Hooks. These will handle the wallet connection and the communication to the RPC layer for us. So when it comes time to connect to our program and submit instructions or read from the accounts, we'll be using a TypeScript client that will be generated from the Kodama IDL library. Transactions will be sent to an RPC on DevNet, and our Anchor program will take care of acting on the different accounts and the PDAs. One caveat that I would like to discuss is that this is not a production-ready market. The use of an oracle would typically be recommended to resolve the markets, as it would build trust in the process. But in our implementation, the market creator is the person responsible to resolve the outcome. As you can see, we've kept our account design pretty simple in this implementation. Each market will be a PDA, so that we can easily reconstruct them on-chain, and each position holding a user stake will also be a PDA. Our whole design will contain a simple count of 4 instructions. Create market initializes a new market with a question that is yes or no. Place bet takes a position on either yes or no. And then resolve market is for the creator who declared the market to resolve the outcome. And claim winnings will allow people who've won money to claim their payout. The beauty of Solana programs is that these 4 simple instructions can be composed into a fully functional prediction market. At this point, you should have a clear mental model. Our market is 2 pools, our market account, and a handful of instructions that move lamports around with strict rules. Nothing magical, just constrained state transitions. That's why Solana is a great fit. It makes these tiny frequent stakes cheap and fast while keeping everything transparent. In the next part, we'll get hands-on with the on-chain program. We'll define the account data, derive PDAs, and write the instruction handlers with the guardrails that prevent late stakes or double claims. We'll also talk about the trade-offs we're making, like creator resolve outcomes, and how we might upgrade this in a future production system. Once the program is solid, we'll back up the stack, we'll wire the UI with a generated client. Let's start building. Alright, before we write any code, we need to decide what lives on-chain. On Solana, programs are basically pure functions over accounts. Each instruction takes accounts in, reads them, and writes them back out. So the account layout is the real API. Get that right, and everything else becomes straightforward state transitions. For this build, we're keeping it minimal. 2 accounts, market for global state, and user position for a single user's exposure. No order book, no price history, no off-chain reference, just the data that we need to validate, positions, and pay people out. That's the whole idea. Alright, so we define these in state.rs, we have the account macro, and we have the derive init space macro. Just a quick note. The init space matters because Solana really allocates spaces up front. So if you go too small, your transaction would fail, but if you go too big, you're gonna burn fees forever. So with init space, essentially what happens is that Anchor will do the sizing for us, and we don't have to care about it. Alright, so here we're going to go a bit over how we did the actual protocol in the backend. So we're going to be going over the state.rs, where we define the different accounts that we'll be using in our prediction market. The first one I want you to take a look at is this market account. We have a little bit of information on it. A few things that I think we should look at is that we have a creator. This is the person that's actually created the market. So the person who really creates a question, sets, the yes or no, every detail about the prediction market, the specific question, it is this person who took this action. So we're storing the creator's public key here. We also have a market ID. This is interesting because we will be having multiple markets, so we want to store all of these as a single ID so that we can differentiate them. Another important one, I am highlighting here the question part. We have to put a maximum length because we need all this data to be known ahead of time. If not, we'll be paying too many fees. So I put a length of just 200 characters. This will keep the question pretty interesting. It will also ensure that we have a maximum, so this way you cannot have a full novel. When you, for example, some people might want to do really complicated prediction markets, but for a good UX, you should keep things light, so maximum of 200 characters should be pretty good. So resolution time is the next thing we're going to have a look at. It is an I64 to store the actual time when the question will end. As an example, you could not really keep that open forever. People will want to see if they won, if they were right on yes or no. So the resolution time is the moment where the market stops, where we're going to really say, this is finalized. After tomorrow, you cannot take any more position on this. And then we are storing the yes pool and the no pool. So this will be where we store the full amounts. For example, more and more people are going to take participation on yes and on no. And we actually need those later on to do the calculations. For example, when yes has 1 and we need to know who took a position and who can get the distribution of the pool. So we're keeping the total amount that people are putting on these yes or no options. And now going over at the end, resolved. Resolved is pretty simple. It really says, has this been closed? So we have I think one specification is that the resolution time is the moment where you cannot take a position after this. But it could be that the question needs somebody to verify if the price really was over 100,000 as an example. So the resolved is when the person closing the market has resolved it. We're going to flip this to true. And the outcome will simply be if yes or no as 1. And we are keeping the bump simply because this will make it easier for us to get back our accounts. Let's go now scrolling down to the user position. What makes this a really simple design is that each user will have its own position, so its own account. And in there, we'll have to link it to the actual market. So if I'm a user and I'm taking a position on the yes pool, I need to know exactly of which market, on which question I'm answering. I really want my stake to be put on the right place. So I'm going to put this here on my user position so that I can link both a bit later. We're going to keep the user here just for simplification so that this user position, we're easily able to match it to the actual user who took it. And we'll have a yes amount or a no amount. This will have to work a bit in the constraints because we will want a user to really put a position only on yes or only on no. So we'll work on this a bit later. And lastly, we're keeping also the claimed status. As an example, if I'm picking my money a first time, I should not be able to take it twice. So I'm going to store this information on the user position account so that we're preventing double claiming. And this is the tour of the accounts we had in state.rs. Let's move on to the next parts. All right, so in this next part, even though we're not going to be building the prediction market line by line, the whole goal of this section is really to show you the interactions between the program, the code generation, and the front end. Even if we're still going a bit high level, we should be trying to understand the business logic of our program, because anytime you're building a full stack application, you really need to understand these interactions between both. It is really what makes the difference between just a quick screen that you put up and an actual thoughtful application that you've built. So we're going to go into lib.rs here, where most of our business logic is living. We saw in the step just before in the video, we saw that we had 4 instructions. We have create market, we have place bet, resolve market, and claim winnings. So obviously creating a market will mean that we need all of the information that we had in state.rs. All of this information, we will need to have it in this function, and we will want to set it onto the account. So going back to lib.rs here, if I expand this section, you will see that the user has to provide a market ID, a question, and a resolution time. All the rest, we're able to actually initialize it ourselves. So a few things that we need to take into account. If I'm setting this resolution time here, I obviously want it to be in the future. For example, creating a market about an event in the past makes no sense. You could be taking position against who won the 2024 election. We all know what happened, so there's no point in actually creating it. So this is why we will use our require here to ensure that the resolution time is actually above the current timestamp. We could go a bit into deeper territory. For example, I could say, give it at least a day or at least an hour, but we're keeping things light and we're just making sure that it is over the current time. And after we are getting the market account and we are setting on this market account all the details that we want, such as the question that we received, the resolution time, and the other parameters we're able to infer naturally. So for example, at the beginning of creating this market, we know that nobody has taken a position on it yet. So we can initialize the yes pool and the no pool, where we're tracking the actual amount of people that have invested Lemports in this, where we can initialize both of them at 0. Obviously, if we're just creating this market, it has not been resolved, so we can set that to false. And in terms of the outcome, we are not ready yet to set the outcome because this will have to happen in the later instructions when we're resolving the market. So I'll go ahead and I will close the create market instruction here. And let's have a look at placing a bet. This is when the user actually takes into their own hands to say, yes, this is true, no, this is true. So we'll have two information into our parameters for these instructions. Obviously, the user will want to put money where their mouth is. So they're going to say, I'm going to put 10 sol on this, or I'm going to put 1 sol on this. And we will have to see if they decided yes or true in their stake that they're taking. So let's expand a bit the instructions here. We need a few basic checks and balances. So we need to ensure that, they're placing an actual bet, so an actual stake. So we need to check that the amount is bigger than 0. And if it is not, we will be returning an invalid amount error simply. We're also doing the checks to ensure that the user are still allowed to participate in that market. So we will be checking that the current time is below the resolution time. Because if it is over, it means that the market is closed. People cannot take a position anymore. Bitcoin has already crossed, the threshold. We cannot really take, we cannot really place at this moment a stake. And lastly, what we're doing here is a CPI to get the user's balance from the user and to get it into the account of the market. So this way, we're actually able to confirm that the user is sending their SOL onto the position that they're taking. And these last few steps, and again, I'm going a bit faster on this. I'm not trying to get you to write line by line this program. Let's really focus here on the architecture. So we're trying to get the business logic. So you could read all of these lines, but what I really want you to focus on is how they will serve into the future application that we're building on the front end and how the little different parts, you have to keep those into account. For example, I showed you here that we're returning errors. When you're building your front end, you will want to know those errors. You will want to understand what to display on the screen if a user is doing something which the program is not set up to do. This is when you should understand what these errors are doing. So all this business logic that we have here is simply just taking care of setting the user stake when they're deciding if they're placing their stake on yes or on no. And if it's not happening, we're simply returning errors and we're finalizing the user stake. Let's close place bet and let's explore the last two instructions that we have quickly. What I think is the two most important ones, which are resolving the market and claiming the winnings. Resolving the market. Here we're doing something actually pretty simple, where we have the actual answer has Bitcoin passed 150, yes or no? Who won the election, candidate A or candidate B? So all that we're doing at this point is that we are setting the actual answer, which means who has won, who has lost. So this is as simple as it gets. And the last instruction that we have is claiming the winnings. This one is pretty simple. We have, again, time logic. So we're checking, okay, is the market resolved? Because if you claim winning on a market which is still open, obviously you should not be getting that money. And we're also doing a require check here because we want to make sure that you've not already taken your money, taken your winnings out of the pool. This is important because we're trying to prevent double spending here. We're trying to make sure that everybody has access to their winnings. And lastly, what we're doing is that we're actually taking out the money of the users, and we are also ensuring that the totals that are left in the pool are properly done. So these are our 4 instructions. As you can see, they're not super complicated. You'll have access to the code if you really want to understand this line by line. What I really want to understand here is that these 4 instructions, we will need to interact with them in the Next.js application. You could wire those manually if you wanted. However, serializing the answers from the front end to the program and using the RPCs to broadcast your transaction, it is actually a lot of manual work. So this is one of the reasons why in the next section, we're going to have a look at a tool called qwe2, which will allow us to create our own TypeScript client automatically from this Anchor program that we've created. Just as a final overview before we move on, I'm just going to go and show you that we also have a few tests here. So these tests essentially ensure the safety of our program. They do not replace a full audit, but you always want, when you're building a full stack application, you want to test every bits and pieces. You want to start from the program, and you want also unit tests on your JavaScript application. This is important because creating a full-on program means there's a lot of moving parts. So you need to pay special attention to these little details. All right, so we're gonna jump straight up into creating our qwe2 IDL client, and I'll see you in the next step. Now we actually have running our full application here. I want to understand a little bit how we actually communicate between the program and the actual front end that we have on screen right here. So I have this Next.js application. We are fetching markets. We're displaying statistics for our users. The key to wiring this up is creating what we call an IDL. So I will jump back into my coding editor right now. We saw in our Anchor folder right here that we had this program with a bunch of instructions, we had a bunch of errors. This is the way that we actually do them on-chain. Consuming this program, you could decide to do it in a Java application, in a JavaScript application, or even in Python. The way that you're achieving this layer of communication is actually pretty important because you need to pass from the different discriminators, the different instruction data with the different bytes in the perfect order. So how do you actually achieve that communication? You could wire it up manually, but just understand that this is error prone. There is a lot of little bytes, a lot of little details, a lot of things to tweak. So understand that doing this manually could lead you to have a bunch of errors in your program, and they're just not fun to debug. They're a great learning experience, but instead we should be using what we call an IDL, an interface definition language. I will go back to my terminal here, and I'm going to run npm run anchor build. You've probably seen that command directly with the Anchor CLI. I've wired up all of this in a full stack application, so I'm using npm to run commands. But what npm Anchor build is doing right now is that it is building our program and it's compiling. But if we go back to our editor here, there is a specific file that I want to look at. If I go under Anchor program prediction market and target, there's a folder called IDL. Let's open it up and open the big JSON file in it. At first glance, this file is nothing special. We can see different names like the market, discriminators, but if we look a bit more closely, there's something interesting. Everything that we've built into our Anchor program, such as our instructions, the errors, everything maps perfectly into this IDL file. For example, under the instruction section, if I open that up, you see that I have my claim winnings instructions here. This is essentially the translation of the logic of your program for other clients to consume. The IDL is essentially a contract layer between the program and the different consumers, and you could have a lot of different consumers. So if you want to go ahead and use this data, use this IDL in something of a more useful format, what you would do would be to wire up a tool like Kodama. With Kodama, you're able to generate a client from that IDL into the target language of choice. In our case, this will be TypeScript, but you could fully decide to go with Go, with Python. There are a lot of different options for your target language. So we've wired this up with this kodama.json file. And the way that we wire it up is that we give it the information of where to look for the IDL file. So if you see this property here, we're pointing to the relative path of predictionmarket.json in the IDL folder. And we're also pointing exactly to where we want this to be generated. More especially, what I want to happen is that I want to generate a client inside my Next.js application so that I will be able to consume it later on. Let's see it in action. So if I go back to my editor here, our last command was npm anchor build. Now we will do npm run kodama.js. What this does is that it reads the IDL and it generates a TypeScript client for us. Let's go and open that client itself. We've put it into application, generated, and then index.ts. Once I am inside my generated client file here, we can actually see that the accounts, the errors, the instructions, and the programs are matching one-to-one the different sections of the IDL. This is important because this is the communication layer between our front end and our back end. As an example here, if I click to definition on my instructions, you can see that the exact same 4 instructions, claim winnings, create market, place a bet, and resolve the market, are matched one-to-one as we wrote them in our program. I'm going to click again to claim winnings to explore a little bit how these files look like. Do understand that you don't have to understand these files completely. There is a good reason that we generate them automatically instead of manually, because this is really error prone. If you did this yourself, it is a great learning experience, but you might not want to directly yourself consume this low-level code, simply because if you're making small errors, it is quite common that you'll see these errors reflected in your front end quite quickly. One important thing to understand about these generated IDLs and the generated clients is that this is a workflow that you have to work in between your program and your front end. If you have a bug, if something is not working when you're decoding accounts, there's a high chance that you've probably forgot to redo your program and redo your generated client. The workflow is generally, you do a change in anchor, you run npm anchor build, and you do again the Kodama client. You could put those in a loop if you wanted. You could do hot reloading as an example, where each time there's a change in your anchor program, you rebuild your client. However, sometimes building a program can take a few seconds to up to a few minutes. So I would say do it manually at first, and once you find your groove, if you feel that you need to automate this, this is a good call. In the next section, we're going to dive directly into the front-end architecture, so I'll meet you on the next steps. In this next section, we're going to see the front-end architecture. In the previous section, we've talked about the program, making the IDL and a client from it, but now we got to put it all together and see how it all works and connects to make a full-stack application. So in my editor here, in my terminal here, I will do npm run dev. I will switch over here to my code editor. So this application is a Next.js application. You have a few options when it comes time to make your front end or for a web application. The most popular ones on Solana are generally React applications. And the most popular React framework for production, I would say, is Next.js. Even though you could be using Svelte, you could be using Vue, but Next.js is where you will probably find the most support in libraries and in content like tutorials on the web. So if we explore here, the structure here, I have my anchor folder, which I'm going to skip because we've seen that a bit before. And I also have my app folder. Inside my app folder, we have our generated client, which we'll be consuming in our pages directly. And if I open the index page here, page.tsx, we're going to see a few things where we have our homepage. Let's scroll down just a little bit. Our homepage, if we see what it looks like in the UI, our homepage has a header where we have the wallet connection at the top. We also have a button to create new markets. And we have this table here where we're showing active markets. We're going to create one in a little bit. And we have these past markets. So this page, as you can see, has a lot of Solana information. We needed to actually wire this to go ahead and start the fetching so that each component can properly display its own data. In Next.js, when you want to provide information to multiple components, you will want to use what we call a React context. A React context is simply a component which is able to pass down its information to all of the child components under them. And if you want to put a context for the whole application into Next.js, you will put it in your layout file at the root of the application. So let's open out layout.tsx here, where we wired all the magic of this context provider. It's pretty light. As you can see, there are the regular Next.js information here. We're not going to look too deeply on those. What I really care about is this provider tag in JSX here. This provider is essentially wiring all of the different communication layers that our components will need in order to communicate with the Solana RPCs. So let's go over and open up that component. So inside providers.tsx, there are two things I really want to look at here. The Solana client NPM package and the Solana React hooks NPM package. A few things to note. These libraries are part of the JavaScript SDK family that are built on top of Solana Kit, but you do not have to write a lot of Solana Kit code manually by hand because these libraries are fully wired so that you can really go and focus straight on your business logic. I'm going to go over pretty quickly what we're doing here. We have this devnet RPC URL, which you will want to have a proper RPC provider if you're going to production with your application. We'll talk about this later in the bootcamp. You will want to create a client where you pass the wallets that you want to support, and you will pass your commitment level. The client, by the way, supports a number of options by default. You do not have to set those. However, you have full control if you decide to do. And lastly, this one is a bit interesting. I'm going to pass in my query configuration. This allows me to set the behaviors of how fast I want my application to refresh and revalidate content on chain. This is pretty fun because some things like a simple CRUD application, for example, would not need to be refreshed pretty often. You would simply create and update data and you'd refresh it when you're changing. But if you're doing something like a prediction market, which have to have a really real-time feeling, you might want to bump those numbers to be refreshing even faster. In our example, we're refreshing every 3,000 milliseconds here, which translate to 3 seconds. You could even get that down if you wanted to 500 centiseconds. We're passing in between units here. But essentially, this wouldn't be near real time. But understand again that there are different options between polling and doing WebSockets, and we're currently doing a polling mechanism here. So once this Solana provider is wired, it will be available to all the children components, such as fetching our markets or fetching the past data for the users. We're going to get back to the UI to understand a bit the components that we're playing with here. So in our first stop, we're going to look at how we can create a market. So in the UI, we simply click New Market. We have to ask a question. For example, will Sol hit $200 this month? And then we decide when it ends. This was the resolution time in our accounts. I will set it for 1 hour. I'll go ahead and I'll create it. Here, this will submit a transaction into the wallet provider that I'm using. In this case, Phantom, but every wallet would work. And once we confirm, we should see this market appear pretty soon. So as you saw, we have around a 2-second to 3-second refresh delay. We could still wire it so that it's manual, like I just did here. But essentially, all of this flow and communication is consuming the IDL that we created. Let's go over and explore a bit the components and see what they're doing. I'll go over to my code editor back here. Let's go to the create market form, which was the first form that we actually created, that we just used to make a market. Let's focus a bit on the different sections here. So I have a few constants here just to make a good user experience. For example, you want to provide information for your users to get started so that they're not lost. It provides them with a good series of information to get started and use your app. And then we're consuming a few React hooks, such as use the wallet connection. This is simply because we need to ensure that a user is properly connected before using that component. And we are using use send transaction. This will be needed when the user is actually submitting the creation of the market. And here, one part that I want to get your attention on is that we have this handle create function here, which is wired up to the submission of the form. There is one special place that I want you to have a look at. You see this get create market instruction async. That was a mouthful to say. This is coming from my Kodama IDL. So if I click to definition here, you can see that this is all the code that was generated for me that I did not have to write by hand. This really makes everything much easier to do, simply because by passing my arguments, such as here I'm passing the creator, a tiny TypeScript bug that we're going to have to fix later on, but the code still compiles. As you can see, these instructions, these arguments to the function are really way simpler than wiring all of this manually yourself. There's a lot less problems that you're going to deal with. You simply just have to pass your proper arguments, and all of this will be handled for you. The rest, after we are ready to send the transaction with the send function, which came from the use send transaction hook, the rest is really just wiring up the UI to give a proper user experience. So as you can see, we're doing a bit of UX cleaning. As an example, we're resetting the question to be empty. We're sending the status to say that the market was created. This is all the behavior that we're not going to go over. We're going to have deeper videos on the Solana YouTube channels about doing a proper UX. We're simply trying to understand the flow here between submitting data on chain and actually having reflect in the UI. So all of these little details, they are mostly to give your users a better experience, such as loading times, such as really reflecting the data and refreshing the data that you're seeing. So this was for creating the actual market. Once you've created it, what will be really important will be to fetch it and display it to the user. So I'll go back to my code here, and I will go to this marketslist.tsx file here. All right, so inside our marketslist.tsx file here, what is really important to understand is that we are fetching the markets. We're doing a little bit of filtering by active and by past markets. For example, if a market is still open and allows a user to take a position, we're good on it. We're going to display it as the active one. And for past markets which have resolved, which are in the past, for example, the 2024 presidential election, we're going to put them in this past section. What I want to have a look at here is this use program hook from the Solana React Hooks library. So a program has different accounts. The use program accounts will give you directly access to fetching all of the on-chain accounts directly by passing just a little bit of information, such as the program address and how you want to encode and decode these. We still openly have work to do on making this easier. This will probably improve a lot by the time that this bootcamp is released. So please go ahead and look in the code. You should probably see something much easier than this on screen. But for now, just understand that the best way of doing this is by consuming these use program hooks, and that things will be much simpler pretty soon. And then everything that we're doing, if I scroll down, is logic around changing the tabs between the active and the past markets. But I want to bring your attention over the rest of the UI. So I'm going to get back to my application here. Some things that is always nice to give to your users is data around all of your interactions with your program. So this activity tab here that I've just clicked on, as you can see, is pretty data heavy. And we are still doing the same accounts reading to provide all of this data. All we're doing is simply doing more advanced React filtering and animations to give users a bit more data. And all of this is really possible because I didn't have to write by hand all of the IDL and the generated client. This would be way more difficult if we were writing and wiring all of this manually. So when it comes to really doing this full stack communication between your program and your front end, what you're looking for is a smooth experience for your users. you should try and build applications which make it feel like the blockchain is just erasing itself. You're trying to achieve a point where, yes, users are connecting their wallet, or maybe they're even connecting with social login, but you want to get to a point where this is easy and pretty seamless for your users. And the current libraries are getting much better at doing this. For example, this refetching in providers really allow you to create these kind of applications where everything is live and refreshable for your users. In the next part, we're going to go over the different problems that we had and how you could expand upon this project. All right, quick but important section. This is a tutorial build, so we made a bunch of choices that keep the code simple. Some of these choices trade off decentralization or product features. That's fine for learning. But you should know exactly where the shortcuts are. We'll go through the main design decisions, the protections we did add, and the obvious upgrades that you would have to make if this was a real product. The biggest one is resolution. In our build, the creator decides the outcome. That keeps the program tiny, and it avoids integrating an oracle, which is a way of getting data from outside to on the chain. But it creates a trust issue. In production, you would want to add an oracle or even multi-signature so that no single party can manipulate the results. We also had to make a trade-off with polling. It's easy to implement and understand, but it adds a bit of latency, and it's a bit heavier on the RPC load. So if you want a real-time user interface, you would use WebSockets or an indexer. Also, all or nothing bets keeps the math clean, but you cannot do partial exits, cash outs, or liquidity. That makes the program easier to reason about, but it limits really what traders can do. And most on-chain activity is usually people trading. And finally, we skip fees. This keeps the math pure and the example clear, but it also means that there's no revenue or sustainability for the business. In production, you will want to add a small fee on each person taking a position or on the winnings, simply for production. Let's also have a basic look at the security that we built in. It won't be perfect, it will not replace an audit, but here are the minimum protections that you want to add into any prediction market. The arithmetic checks are there to really prevent an overflow attack. In a pari-mutual system, overflowing a pool can change implied prices or even allow free bets. Using checked math is boring, but it's critical. We also gate claims with position.claimed. That makes claims idempotent and prevents double spending. The resolution time check prevents late position, and the creator check prevents random signers from resolving the market. Notice what's missing. We do not prevent a creator from resolving early with the wrong outcome, and we don't prevent griefing with spam markets. Those are product and governance problems that more mature code bases would actually have to handle. We also don't do anything about front running or transaction ordering. On Solana, that usually shows up as users racing at the end of a deadline, but for a tutorial, it's really fine. If this was production, we'd have to do a bit more work to cut everything and put everything together properly, but this is a tutorial and it's completely fine. So what could we be adding to make this a bit better? First, we could add decentralized oracles. Switchboard or Pyth really come to mind. We could also add a fee so that the protocol is more mature and sustainable. Another one for people actually interacting with these markets would be partial position exits or better liquidity. And obviously, like we discussed in the beginning, multi-outcome markets that go beyond the simple yes or no question. If you really wanted to keep going, I would say work first on oracles. They're a bigger upgrade, but they're the most logical one to do. You could also look right next to this after fees to make a better protocol really work for you. So the takeaway is simple. The core is solid, but this is a learning-focused version. If you treat it like production, you will want to harden it. That's normal. Engineering and creating projects is all about a balance between solid features and security. Keep your users in mind, take the decision, but continue learning. All right, let's wrap it up. If you've made it this far, you have a full-stack prediction market running on Solana. You built the on-chain program, you generated a type-safe client, and you wired it up into a React frontend. The best part is that the whole thing is small. There are only a few instructions, a couple of accounts, and a simple UI. But the architecture can really scale. You can add features without changing the core flow. Quick recap. We talked about where prediction markets work, why Solana is a good fit. We built an on-chain program with 4 instructions. We also generated a client from the IDL so that our frontend is all wired up and type safe. And we made our user interface connected to the backend, and we fetch transactions and do it the full flows. In the last section, we simply discuss the security trade-offs, the architecture, and how you can improve things going further. So the full picture. First, a user interacts with a React component. That component calls the generated instructions. We have a wallet that signs transactions and sends them to Solana. We also have our anchor program that validates, mutates the account state. And lastly, our front end pulls and updates the state, re-rendering our application to make this all come alive. That loop is the entire app. The user clicks, the client builds an instruction, the wallet signs, the program updates the state, and the UI refreshes. Once you internalize that loop, you have pretty much everything you need for Solana development and becomes easier. A few takeaways here. Programs are stateless. It's the account that holds the state. PDAs enable trustless escrows, and no private keys are holding funds. Code generation eliminates serialization bugs and make type-safe front-ends by default. The IDL is the contract. In between the chain and off-chain is the connection flow. And if you remember just one thing, remember this. The program is small, the accounts are the truth, and the client should be generated. This combo keeps you sane as your project grows and really scales easily. Also, don't underestimate the value of just keeping things boring. The simpler the state model, the easier it is to debug and really to extend it later. Most production bugs are not clever things, they're really just mismatched assumptions between the layers. If you want to go deeper, Anchor and the Solana Cookbook are the best starting points. Kodama is a bit more high level, but it's worth exploring if you want to build program and you want to keep your front end clean. If you're new to Solana, especially keep time rethinking about your PDAs and account ownership. These two concepts show up everywhere. Once they click, everything will just feel way less mysterious. So the next steps for you would be simply cloning this repo locally, try modifying a few validation, see if you break anything. You could also be adding new field to the market struct. You could trace the codegen output. All of these exercises force you to touch the full stack, which is a real skill you want here. Change Rust, regenerate the client, update the UI, watch how the whole loop works. If you want a bigger challenge, try adding an Oracle-based resolution flow or a tiny feed to the protocol. Both changes will touch every layer, which is great practice. Thank you for watching. If you're building something cool with this, I'd love to see it, tweet us on it, and just have fun building. Now we're going to talk about something that does not get enough attention in the Solana ecosystem: production readiness for application. You know, there's a massive gap between building a proof of concept that works on DevNet to really launching something that can handle money, users, because there are real consequences if there's bugs. Honestly, this gap has burned a lot of dreams. So let me start with a story that might sound familiar. You're building this amazing payments application, maybe it's a checkout system, a marketplace, or something with some Fordham subscription. You've tested it locally, you've deployed to DevNet, and everything works beautifully. You're ready to flip the switch, and you start processing real transactions, and then it hits you like a truck. So suddenly you're dealing with questions that you never thought about. Let's go through them. What happens when the RPC endpoint goes down, and you're in the middle of making a payment? Or the transaction is stuck in the mempool and it expires? How do you handle priority fees when a network gets congested? Or what happens if somebody tries to pay you, but the token is actually fake, but looks exactly like USDC? So how do you keep also your sending keys secure when you need to have them accessible by your backend service? This is not theoretical. These things will absolutely wreck your launch if you don't handle them properly. And the tricky part is that most of these issues don't show up in testing. They only emerge when you're live, there's real money on the line, and people are expecting things to just work. So let's break down what production readiness actually means for Solana applications. Because it's not just one thing, it's a whole system of consideration that work together to create a reliable, secure, and maintainable infrastructure. So first of all, let's talk about SOL. This seems basic, but it's critical. Your mainnet wallet needs actual SOL to pay for transaction fees and rent. Not a lot necessarily, but you need to think about this operationally. How much SOL do you need? Well, that depends on your transaction volume. But you should be thinking in terms of coverage fees and thousands of transactions, plus rent for any accounts you're creating. And here's the thing that nobody tells you. You need a system to monitor this balance and alert you before you run out. Running out of SOL mid-operation is embarrassing and completely avoidable. Now, RPC configuration. This trips up a lot of teams. During development, you're probably used to using the Solana RPC endpoint. They're great for testing, but they're not suitable for production. They're rate limited, they can be slow, and they don't give you any guarantee of uptime or performance. For production, you need to configure your own RPC endpoint. This normally means running your own validator, or more commonly, getting a dedicated provider like Helios, Triton, QuickNode, and way many more. There are great services out there, so use them. But here's the crucial part. Whatever RPC setup you choose, it shouldn't be a public endpoint that anyone on the internet can hit. Your production RPC should be private, authenticated, and locked down to only your services. Why? Because there's rate limits, security, and you want to control exactly how your application interacts on the network. And speaking of RPC endpoints, you need a fallback. Your primary RPC is going to go down at some point. It will. There are great resources, but if there's a maintenance window that you forgot about, or there's a DDoS attack, maybe even a submarine cuts an underground cable, that can happen, and it is a real problem. Whatever the reason is, you need a backup RPC for your application that you can fail over to. This means your codes needs to be designed with multiple RPC endpoints in mind from day one. Let's talk about priority fees. It seems optional, but when it becomes actually needed, it is critical. Solana's transaction processing is a first come, first served by default. So when a network is busy, priority fees lets you jump the queue right up. For applications that are critical like payments, this can be the difference between a transaction going up right away or sitting in the mempool and waiting for seconds, not minutes, but it could delay your user experience. The smart approach here is dynamic pricing. Don't just hard code a priority fee value. Implement logic that looks at the current network prediction and adjust the priority fee accordingly. When a network is quiet, pay the minimum, you're good. When things are congested, pay for what you need so that your transaction goes in. Your users want your payments to work. They cannot wait for seconds at the coffee shop. So spending an extra fraction of a cent on priority is worth making the experience better. Now we go into the retry logic, and it gets interesting. Solana transactions can fail for all sorts of reasons. Maybe the block hash expired before the transaction was processed, or maybe there was a temporary network hiccup. Maybe the RPC endpoint had a momentary issue. Whatever the cause, your application needs to handle these failures gracefully. But here's the tricky part. You can just blindly retry after every failed transaction. Some are permanent, maybe there was a real error in the code, or maybe somebody tries to pay you with an account that they don't control. Retrying won't help. If there are insufficient funds, retrying won't help again. Your retry logic needs to be smart. You need to understand what is a temporary failure and what is actually a bug that is preventing your user from doing the real transaction. And there's another layer to this block hash expiration. Every Solana transaction includes a recent block hash, and it's only valid for 150 slots, in today's conditions, 60 to 90 seconds. If your transaction doesn't land within that window, it expires. Your retry logic needs to detect this and create a fresh transaction with a new block hash and retrying instead of using the old one. Confirmation levels. This is really a concept that trips people up because it's different than other blockchains. On Solana, a transaction can be confirmed at different levels: processed, confirmed, and finalized. Processed means it's been included in a block. Confirmed means that the block has been voted on by a supermajority, and finalized means that the block is rooted and cannot be rolled back. For most applications, confirmed is the right level to wait for. It's fast, takes a second or two, and the probability of rolling back is really low. Finalized is more secure, but it's longer. There's 32 slots, around 13 seconds around the current conditions, so you need to choose based on your use case. High-value payments might be justifying waiting for finalize, but regular payments don't. Error handling really deserves its own deep dive also, because Solana's error messages can be cryptic at times, and your users don't want to decipher them themselves. When something goes wrong, you need to catch the error, understand what it means, and present it as something useful to the user. Transaction simulation failed is not helpful. Insufficient funds to complete this payment is actually working well. Think about all the common error cases like insufficient SOL for fees, insufficient token balance, invalid recipient address, slippage tolerance exceeded if you're doing swaps, account not rent exempt. Every one of these should be handled specifically with a clear message. If you're dealing with gasless transaction when you're covering fees for your user, there's another level of complexity added. You need a robust system to sign and submit transactions on behalf of the users while keeping security and preventing abuse. This typically involves some kinds of transaction relay service with rate limiting and fraud detection. Now, token verification. This is critical and often overlooked. If your application accepts payments, for example, USDC, you must verify that the USDC payment that is being sent is not a scam token created to look just like it. Check the mint address against the official list, and don't trust what the token calls itself. Verify the actual on-chain address of the mint token. Security is paramount. Your private keys are the keys to your treasury. Literally, they should never, ever be stored in your front-end code anywhere a user can access them. Backend only, encrypted at rest with proper key management practices. Consider using a hardware security module, HMS, or a key management service, and implement the principle of least privilege. Keys should only be able to do exactly what they need and nothing more. Actually, let's expand on that. You should have separate keys for different operations. Don't use the same key for signing transactions or for controlling your treasury. Set up a proper key hierarchy with hot wallets for day-to-day operations and cold storage for the bulk of your funds. And please back up your keys securely. Multiple backups in different locations, proper encryption. Now, transaction monitoring and alerting. You need to know what's happening in your application in real time. Set up monitoring for transaction success rates, average confirmation times, failed transaction patterns. If something is going wrong, you want to know immediately, not when users start complaining. Build dashboards, put up alerts, and integrate with incident management systems. And finally, load testing. You cannot skip this. You need to test your system under the load that you expect to handle, and then test it under way more load than that. What happens when you go to processing 10,000 an hour, 1 million? What's the bottleneck? Is it your RPC connection, your database, signing service? You need to find the limits before your users find them themselves. Production readiness, it's not about checking boxes on a list. It's about making a system that is reliable, secure, and maintainable under real-world conditions. It's about thinking through the failure modes, the edge cases, and respecting the fact that you're handling money and users' expectation. The good news is that this is doable. Teams successfully launch applications on Solana all the time, but they do it by taking these considerations seriously from the start, not adding them on as afterthoughts. So as you're building your next application, keep these principles in mind. Your future self, your users, and everybody will thank you.